Today we start section 4.7 and the topic is optimization problems. So for these optimization problems, we basically want to maximize or minimize some variable quantity. So this is a challenging section. A lot of it, once we come up with our mathematical model, then the rest of it is a lot like 4.1 and 4.3, but the tricky part is coming up with our model, where in 4.1 and 4.3 they would give us a function and they may give us an interval and they ask us to find the absolute maximum or absolute minimum value on that interval of the function. Well, this time we have to come up with our function and think about our intervals, and that's the tricky part. So there's three sections that typically give Calc 1 students the most trouble. One of them is delta epsilon proofs, which we didn't cover, and it's being covered less and less in calculus classes. The other one is related rates problems, which you guys may remember. Those can be a bit of a handful. And then this is the last one, optimization problems. But of the three, in my opinion, this is the most important problem. The optimization problems are the most important because these are the closest type of problems to what you'll see if someone pays you to use math to solve problems. So engineering problems almost always have a cost associated with them, and almost always that's going to be an issue. You can't always find the absolute best solution because that may involve crazy amounts of cost. So you find the best solution with your constraints. And so optimization problems, although they're going to be simpler than the ones you run into when you're done with college and you're getting paid to solve these problems, but they will be kind of a simple version of that. So to start off, we're going to start with a problem that you may have seen in algebra. This is kind of a classic problem. This particular problem is solvable using algebra as long as you have some sort of graphing calculator. So I'm going to look at the solution first using a graphing calculator, and then we'll look at the solution using calculus, where you don't need a graphing calculator. But this is a pretty classic problem, so I'm sure some of you have seen this before. But the idea is we have got this box here, 18 by 24 box, and we want to, we're going to make we've got an 18 by 24 sheet of cardboard, and we want to turn this sheet of cardboard into a box by cutting out corners and then folding the box along those edges. So we're going to cut out these little pieces, these little square pieces of the box. I guess this would actually come up here a little bit more. It's going to be square. So these are going to be X by X. All are going to be the same. And so we want to just make a box by cutting these out and then folding along the ends here. So we cut these out, and then fold up here. So this part right here would be the edge of the box. This part would be the edge, and so forth. So we need to know, we're going to cut out squares of equal size from the four corners. How large should the squares be to maximize the volume of the box? So we want to maximize the volume. Well, you may notice one thing, like there is a bound on this X. Like if this is 18 inches here, the most we could cut out for X would be 9 inches, because that means this box would be cutting this right in the middle. So there'd be nothing to fold up. So we'd have a volume of 0. So I'm going to add this, although we don't really need it, but just because we will use this in future problems, I'm going to mention this is actually a constraint. So there's a constraint, and the constraint is that X has to be between 0 and 9. right? I mean, if x is 0, that means we're not cutting anything out. So when we fold up the edge, there would be no edge, so the volume would be 0. And at the same time, if we cut this, if we made this x be 9, you know, if we go out 9 inches and cut 9 inches, then we fold it up, we have another volume of 0. So x is going to be somewhere between 0 and 9. And we can use that when we're going to use this, solve this using algebra, because we're going to use a graphing calculator. We know that x is going to be between 0 and 9. So that's a constraint. In reality, constraints will often have to do with financial constraints, but there are time constraints, material constraints, and all kinds of other constraints. So as an example, this is not related to this problem, but let's just say your boss says, hey, we want you to come up with a way to save money in constructing a soup can. So you've got this soup can, and it's got certain dimensions, and typically the material on the top and the bottom will be a little different than the material on the sides. Maybe it'll be a little, maybe even the same material but a little bit thicker because of handling costs or handling treatments, that if these are stacked on top of each other, or for the connection, they have to be connected along the joints here. So often, as you could just know from being alive and using things, cans will have different materials or different thickness of the materials on the top and the bottom as you do on the sides. So your boss says we want to cut down on the cost of the containers, so what can we do? And let's say your solution is this. You're like, hey boss, I've got this solution. This will save us quite a bit of money. It holds the same amount of material, but it's going to be shaped like this. Well, so you can imagine some problems. These are not going to stack very well, at least not the way that we normally stack them, where you have your label here, you've got your product and some information. Well, that's not going to really work. You're going to have to redo that entire thing to make it work on this weird shaped soup can, and also just for shipping and handling and for other reasons this might not work. Boss might say, yeah, well, we would save some money, but that's not going to work. So there's all kinds of constraints, and we're not going to have crazy constraints in these problems because these are basic problems, but there are a lot more constraints when you're done with calculus and you're working on real problems in design and engineering. But anyway, back to this problem here with the box. What we can do is think about, if this side is 24 inches, but we're cutting out this x by x inches, so what we would really have left right here, it's not going to be 24 anymore. It's 24 minus this x and minus this x. So really this dimension now is going to be 24 minus 2x. And with something very similar right here, this is going to be 18 minus 2x. So when we think about the volume of this box that we're going to have, we know volume is length times width times height. We've known that since elementary school, volume of a box. So in this case, if we put these pieces together, we would have the length. Again, these don't matter what you call them. It doesn't matter if you call this the length or the width or the height. You can see the height. When this flap folds up, the height's going to be x, right? When this flap here folds up, the height will be x. So you could think of the volume as 24 minus 2x times 18 minus 2x times x. That's going to be our volume. So if you FOIL these two, FOIL this binomial times that binomial, and then distribute this x through, and you'll want to do that just for a little practice, but if you do that, you're going to get, when you're all said and done, and if you put these in order from highest power to lowest power, you should get this. So remember, when you're watching these videos, pause occasionally to verify that these things are true, and then just press play to continue. So this is the volume, and what we want to do, we want to maximize the volume. Now, the only real constraint we have right now is this, right? This is our only constraint. We know x has to be between 0 and 9. So this is our mathematical model for the volume, but this is a cubic. This is going to go on forever, right? The domain of this function is all real numbers. But as far as we're concerned, we don't care about the entire domain of this function. We care about this little window of this function. All we care about for this function is where it applies to our mathematical model of the volume. And that's on this window right here, 0 to 9. So maybe the maximum value occurs at 20, when x is 20. Well, it doesn't matter because it doesn't make sense for our problem. For our problem, we only care about x between 0 and 9. So if you're in algebra class, or if you saw one like this in algebra, what you would do then is you would go to your graphing calculator. Because in algebra, we don't really know how to maximize this without looking at a graph. So in algebra class, we would then go to the graphing calculator, and we would plug this function in for y1, and then we would set our window. And looking at our window, we know x has to be between 0 and 9. So just to kind of pick an easy one, I just went 0 to 10. And then y, if you play around with this a little bit, you'll see that for y, for this will be y, right? On a calculator, it would call the volume y. This can go pretty high. So 0 to 1,000 is probably a good window. So if we plug this in for y1, and then go to your window, and on your window, and your calculator, let's do this. Let's x go from 0 to 10, y go from 0 to 1,000, and I put a I put a tick mark every 100 here. And got some pictures here. I'm going to try to get some of these out of here. So here is the graph, and here's the window. See the window? That's the window you want to use. It's covering up the 0 on the x minimum, but 0 to 10. Here is the graph. Make sure that none of your plots are highlighted. If they are if you have any of these plots highlighted up here, just go up, use your cursor up to that and hit enter to turn them off. We don't want any plots highlighted. And then we need one more. See if I can get the picture of the graph. Okay. All right, so if we were in algebra class, we would look at the picture here, and we would try to find this peak. Remember, this is our volume. This is the volume of our box between 0 and 10. So you can see the peak is right here, right? Because we put y equals, or y1 equals. So this is our volume curve. So if we're in algebra class, you want to see where this peak volume is. So on the calculator, we go to the second button, second trace, which gives us So you basically press second and then trace. And when you do that, we want to go to maximum. So then you hit, on my calculator, it's number 4 for maximum. And it wants a left bound and a right bound. So just move your cursor to the left. I know most of you have done this plenty of times. Move it to the left so you're on the left side of the hump. Anywhere on the left side, hit enter. Then move your cursor to the right side of the hump, anywhere, and hit enter. And it's going to ask for a guess. You can just hit enter on that guess. It just needs a starting point. Any starting point will work. And then it should give you the maximum. So when I run it on my calculator, it tells me that the maximum it says X is roughly 3.39 and Y is approximately 655.0. So using algebra to answer the question, how large should the squares be to maximize the volume of the box? The squares should be, just from looking at this, the squares should be roughly 3.39 inches by 3.39 inches. And if they ask what the maximum volume of the box is, this would be the maximum volume. And what would the units be? It's a volume, right? Length times width times height. Each of those dimensions, length, width, and height, are all in inches. So when you multiply inch times inch times inch, you get cubic inches. So the maximum volume would be 655 cubic inches. So if all we had was algebra and a graphing calculator, that's how we would solve this problem. But as you guys know, we have more than algebra and a graphing calculator. We have calculus, so that's how we're going to solve the problem next. So using calculus, we can start with our volume. We would calculate the volume the same way. So come up with the same mathematical model as before. So now we're going to use calculus. Oops. Let's try that again. Now we are going to use calculus. So we start off with our same volume. We had volume equals 4x cubed minus 84x squared plus 432x. So what we want to do with calculus is we want to find the critical numbers. We're looking for critical numbers because those will give us the peaks and the valleys in the graph. And of course we could check the endpoints, but usually in optimization problems the endpoints are not going to help us. So the endpoints here would be like x equals 0 and x equals 9. And we can see in either of those cases the volume will be 0. It's easy to see for 0 if you plug in 0 here. But if you plug in 9 for x, you'll also get a volume equals 0. So let's go ahead and take the derivative here. So we want to find v prime, which is going to be equal to 12x squared minus 168x plus 432. We want to set this equal to 0. We can see that because this is a polynomial, polynomials are really nice functions to work with because they're continuous everywhere, they're differentiable everywhere, and they actually can be integrated anywhere, which we'll see later. So they're nice to work with, but we need to solve this. So the first thing that I'm going to do, just to make it easier, is I'm going to divide each side of this equation by 12, and then we'll get x squared minus 14x plus 36 equals 0. And it would be really nice if this factored, right? But optimization problems sometimes give us our first dose of reality, and the reality is when you have a real mathematical model, it hardly ever factors nicely. So we're going to have to use the quadratic formula. So just for a little review here, if we have ax squared plus bx plus c equals 0, this works for any second degree equation, right? Which we've got here, second degree equation. And the quadratic formula says that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully you guys were sufficiently nagged in your earlier days of your math education so that you have this memorized, because it's a nice one to know. So to solve this equation using that, you just go through a little tedious calculations here. And we will get x equals negative b plus or minus the square root of b squared minus 4ac. Now, if you haven't done this in a while, one thing that I'll mention here over 2a is this. This thing here is always going to be positive. So don't just punch in this. If you just punch in your calculator negative 14 squared, you're going to get the wrong answer, because your calculator knows order of operations, and it's going to square a number before it even considers a subtraction. It's going to treat a negative like a subtraction. So this is going to give us a negative number, which doesn't make any sense, because b squared, when you square b, it's always going to be positive. So when you're doing the quadratic formula, either do this or just ignore the negative and square the number, because we know it's going to be positive anyway. So this will give us 14 plus or minus 196 minus 144 all over 2, which is equal to 14 plus or minus the square root of 52 all over 2. At this point, we could plug this in the calculator, but I know some of you are going to be thinking, now wait a minute, Kurt, 52 has a perfect square factor. So some of you will immediately send hate email if I don't keep going here to get the exact answer. So since the square root of 52 equals the square root of 4 times 13, and that's equal to the square root of 4 times the square root of 13, that would be 2 times the square root of 13. So we could write this as 14 plus or minus 2 times the square root of 13 all over 2. And now we have 3 terms, all of which are divisible by 2. So we could write equals 7 plus or minus the square root of 13. Now once you plug this in your calculator, we're going to get 2 answers. This gives us an answer of 3.39 and 10.61. So remember, these are both answers to our original equation, but only one of them makes sense for us because we have a mathematical model we're working on. This one doesn't make any sense for our situation. Only this one does, because remember, x can't be bigger than 9. So this isn't going to work for our model. So we have our dimension of x, 3.39 inches, which is what we got last time using algebra. So if we plug this into our original volume formula, so remember our original volume formula, let me rewrite that one a second. Whoops, that's not what I wanted. So our original volume formula said this. It said v equals 4x cubed minus 84x squared plus 432x. If we plug this in for x, plug that in for x there, then we'll get our maximum volume, which we know is about 655 cubic inches. But so we get the same answer using algebra or calculus, but of course our approach will be calculus because it works in a lot more types of problems. Algebra is somewhat limited, and we had to rely on a graphing calculator. But I just want to mention one more thing. This is just a little note. A little note here. If we take the second derivative, so look back at our original derivative. Our original derivative, v prime, was 12x squared minus 168x plus 432. If I take the derivative of that, we get 24x minus 168. And what I'm mentioning here has to do with the second derivative test. So if we take the second derivative and we plug in 3.39, so if I plug in 3.39 here, 24 times 3.39, even it just, you don't even have to plug it in. Just think about if we plug in 4, 24 times 4 is going to be smaller than 168, right? So definitely when we plug this, we are going to get a number that's going to be negative. So if I plug in 3.39 into the second derivative, I'm definitely getting a negative number. So think about the second derivative test. Second derivative test is negative. When you're feeling negative, you feel negative, you have a frowny face, which means the original graph, since the second derivative is negative here, it means the original graph is concave down, which means we have to be at a maximum, right? This is the original graph around this area. Now we know at 3.39 the original graph is flat, but this is saying the original graph in this area is concave downward. So that means it's it flattens out right here at 3.39, and the graph of the function, the volume function, is also concave down. So if it flattens out here and it's concave down, that's got to be a maximum, right? So that's the second derivative test. You could say, therefore, the volume is a maximum here, meaning here at 3.39. The next two examples here are a little, they're more basic than a lot of them, but it'll give us an idea of how to get started on these. This first one, we've got this person, Ronnie, has 200 feet of fence and she wants to build a rectangular garden adjacent to her garage. What dimension should the garden be to maximize its area? This problem that Ronnie comes from, a student of mine was complaining because he told his girlfriend he would go see this movie with Miley Cyrus in it called The Last Song. And her name was Ronnie in there, so I did this as a little inside joke for him because he said he hated the movie, but he had to go because she went hunting with him or something. So it was like some kind of agreement they made. But anyway, if you've ever seen the movie, that's where this name comes from. So Ronnie has 200 feet of fence. So I'm just going to get a picture here. We've got, let's say we've got this garage. We'll use some colors here. Here's the garage. And then we've got this rectangular garden adjacent to the garage. So it's a rectangular garden. So we've got something like this. So here's the garden in here. What dimension should the garden be to maximize its area? Well, since it's rectangular, these will be the same. I'm just going to call it X, and then there's this Y, which could be different. So what we want to do is think about what we want. Okay, we want to maximize the area, right? The area. So we need to start off thinking, what's the area here? Well, the area of this picture is going to be X times Y. So we want to maximize this. And one thing we're going to notice with a lot of these is when we look at this, we look at our variables, we've really got 3 variables here. But what we want to have is only one independent variable. So we want to find the area in terms of one variable, not 2. We've got 2 variables, which is very bad. So you want to fix that. We've got 2 variables. When we see 2 variables in Calc 1 or Calc 2, it makes us sad. We want only one variable. So we need to somehow get rid of one of these. The way we do that is we need to find some other relationship, some other relationship between X and Y so that we can use that relationship to eliminate one of these. And they tell us up here that Ronnie has 200 feet of fence. So that means if we add up all these 3 sides, we get 200 feet. That's the other relationship we need. So if we add up those sides, we get 2x plus y. We know that is 200. And this is also, we could call this our constraint, right? We only have 200 feet of fence. We can't have a garden that is 70 acres large because we've only got 200 feet of fence. So this is a constraint, but we're going to use this to eliminate one of these. And it doesn't matter which one. I could solve this equation for x or for y. Typically what you want to do is find the easiest. Looking at this, wouldn't it be a little easier to solve for y? Because I just have to subtract 2x. If I solve for x, I need to subtract y, then divide by 2. So I'm going to solve this equation for y. So to do that, we get y equals 200 minus 2x. And now this allows us to eliminate one of these variables because what we can do is just take 200 minus 2x. Since that's equal to y, I'm going to just plug that in here. So I'm going to come up with a brand new area formula. Instead of x times y, I'm going to have x times 200 minus 2x. So this is our new area formula. The nice thing about this area formula, well, let me just distribute this x through. We get 200x minus 2x squared. This is our area. And we want to maximize this. Should have pointed it out before. This is what we want to maximize. We want to maximize the area. So now we've got one variable, one independent variable, right? One independent variable, just x. That's our independent variable. We have the area in terms of x. And since it's only one variable, that makes us very happy, which is what we need. So at this point, we know what we're going to maximize. We want to maximize the area. And the function that we're trying to maximize or minimize, that's the function we take the derivative of every single time. So just to keep that in mind, because sometimes we'll have these other functions in here, but the one that we're trying to optimize, maximize or minimize, that's when we want to take the area of, take the derivative of to find the critical numbers. So this one's got a very easy derivative. Area prime is 200 minus 4x. We set this equal to 0. 200 equals 4x. Divide by 4 and x equals 50. So x equals 50. So if I look at the original picture, this is 50. This is 50. Then what about y? Well, once we have x, we go back to right here, right? This is our formula for y. Y equals 200 minus 2x. So in our case, y equals 200 minus 100, because 2 times 50 is 100. So that y equals 100. So they said, what dimension should the garden be to maximize its area? To answer the question, the dimensions should be 50 feet by 100 feet. Remember, we want to answer the question. So when you are working someday, being underworked and overpaid, and your boss wants you to solve a problem, you're never going to say, hey boss, x equals 50. It's not going to happen. That'll be part of your work, but you're going to give the boss the final answer in the format they were asking the question in. So remember, don't just say x equals 50. We need to answer the questions to these problems. So the dimensions are 50 feet by 100 feet. And again, just to show that all this stuff is connected, if I took the second derivative, I would get -4. And that's a constant. -4 is less than 0. The second derivative is negative everywhere, which means we've got concave down, which means that the problem that we're working on at that point is a maximum. So we maximize the area. And if you wanted to find the area, you can just plug in those dimensions into the area formula. And I mentioned this before, but in reality, there will be more constraints because there are always financial constraints. Nobody has an unlimited budget. So you would also consider the types of fencing. There's usually a lot more variables involved, but these give us our starting point. And as things get more complicated, we just add on little pieces. So, okay, let's try another one here. find two numbers that sum to 10 and have the greatest product. Okay, so we're looking at the greatest product. So we're going to multiply these numbers together and find the greatest product. So you could just think, well, numbers that sum to 10, well, let's see, we've got 1 plus 9, 2 plus 8, 4.3 plus 5.7. And you could keep on going and just think, now if I multiply these together, I get 9. These together, I get 16. And you could keep multiplying, and that's basically what we're trying to do, but we want to not waste our time like that. So we want to find the greatest product. So this is what we want. Product equals x times y. Our two numbers, we want to multiply them together. This is what we want to maximize. And we also know that these numbers sum to 10. These numbers sum to 10. So we also know that x plus y equals 10. So this would be our constraint. But remember, we want to maximize the product. So this is the function we're going to concentrate on. We want to take the derivative of this one because that's when we want to optimize, we want to maximize. And we use this constraint because right now when you look at this, you notice something about the independent variables. There's too many of them. We've got 2 of them. And we are in single variable calculus, so we want 1 of these. So how do we get rid of 1? This will give us a way to do that. So I'm going to look at this other one, our constraint, and I'm just going to solve it for one of the variables. Again, it doesn't matter. I'll just solve it for y. So y equals 10 minus x. Then I'm going to plug this back in for this y and come up with a new function I want to maximize, which is x times 10 minus x, which if you distribute that through, we get right here. And this is nice because now if you look at this one, we've got one independent variable, just x, and we just want to maximize this one. And now we're ready to go because we've only got one independent variable. So at this point, we can go ahead and take the derivative. So p prime equals 10 minus 2x. Set this equal to 0. 10 equals 2x. X equals 5. So find two numbers that sum to 10. Here's one of them, x equals 5. Well, to find the other one, we just go back here. Y equals 10 minus x. So if I plug in 5 for x, I'm going to get y equals 5. So y equals 5. So the two numbers are 5 and 5. They're the same number. And again, just to verify, and you don't have to verify this with the second derivative, but I'm just going to, just so we can see it works. The second derivative, we go from the derivative to the second derivative, we are going to get a negative 2, which is a negative, which means that this curve is concave downward everywhere. So if you can sort of see it because this is a second degree equation and it opens down, right? So we know it goes something like this. It's a second degree equation opening down, and it can be verified here. The second derivative is negative. When you're feeling negative, you have a frowny face, concave downward. So if we're finding a flat area here, we are definitely going to be finding the maximum. So we answered the question. Those are the two numbers that have the greatest product. So if you wanted to find the product, you just multiply those two together, you get 25, and that's the greatest product. And some of these problems, if they don't have a lot of constraints, you'll see this symmetry. There's a lot of symmetry in these optimization problems when they're unconstrained, like there's not a lot of constraint here. When you start to constrain them, especially with cost, the symmetry goes away. But just plain problems with very little constraint, symmetry a lot of times emerges from these.